All right, let's go ahead and start. Everyone's sitting closer today. It's nice. So, oh, it's fine. You don't. All right. So, okay. So we've been talking about distinguishability measures, trace distance, and fidelity. There are important generalizations of those concepts, the quantum channels, called diamond distance and channel fidelity. I didn't plan on going over them today. Let me just do it briefly so you'll know the concept. So N and M are channels from Alice to Bob. And the diamond distance is a channel distinguishability measure. So what do? You take the distinguishability measure for quantum states and you optimize over all inputs to the channels. And that's the diamond distance. Okay. So we define it as a supremum over all bipartite states. You should think of a diagram like this. Where you just optimize the trace distance. Okay. Supremum is over all input bipartite states, and the reference system can be arbitrarily large. Okay. What you can show is that it suffices to take, the supremum becomes a maximum. The optimizing value is in the set. It's not like in the limit as the dimension gets larger and larger. And it suffices to optimize over pure states where system A prime is isomorphic to A. That means that in finite dimensions, it just has the same dimension. Okay. So this is true, and you can prove that using spectral decomposition, Schmidt decomposition, and convexity of trace distance. All right, I'll just leave it at that. There's another way you can prove it without the convexity of trace distance, just using the fact that all purifications are related by isometries acting the purification system.
States is this distance lower?
Is it what? Lower?
For mixed states. Why that
it's equal. I'm asserting that it's equal.
Okay. I was just wondering why it suffices to solve it for pure states.
All right, let's talk about why that is. So this will be a general mixed state. So, all right, you can purify that. Right? And now these two systems purify this. Okay, so you can purify it, then you can use data processing. Right? So let's consider this. So from data processing with respect to partial trace over this, we get let psi rho be a purification of rho. Right? So this we get from data processing. And you can trace over R prime and R, psi rho. You get a mixed state we'll call rho A. Right? Then you can always find a purification of this where the purified system has the same dimension as A. Right? So call that phi A prime A rho that you can do. And then there's an isometry relating A prime to R prime and R, right? And then that isometry can act on these reference systems that are not part of the channel input. And the trace norm is invariant under isometries.
So choosing a pure state, it's more like a
Pure state does the job.
Okay.
It's
So,
more than a method. Well, it's a computational convenience as well. Otherwise, you wouldn't be able to compute this. R could be infinite dimensional, right? You're going to be limiting finite dimensions.
I was
So,
wondering if pure states are optimal also, but because we cannot achieve the maximum or the supreme using the mixed state. Or we can achieve it with a mixed state.
this is why, right? And actually, this kind of reasoning is important. Like any state distinguishability measure, you can lift to a channel distinguishability measure in precisely the same way, right? We're going to replace trace norm with, later on, we'll talk about generalized divergence. Actually, I intended, I think, to talk about that earlier. But a generalized divergence is just something that obeys data processing, right? And then, you know, it's like, we'll do something like make this bold and then call that generalized divergence, right? And then the only thing we used here was data processing. So, you know, it's a very generic argument and it applies to essentially any channel distinguishability measure. Okay. We spent quite some time talking about operational interpretations of trace distance. The same things apply to diamond distance. So there's, just very briefly, there's a task called channel discrimination. Okay, so I between 0 and 1. This is important for communication. It's important for people who are trying to build quantum radars. They're trying to explore the theory of quantum radars. This applies to that scenario. So the scenario is this. Imagine that, you know, here's Alice, here's Bob. Right? So it's a guessing game. You know, the goal of Alice is to guess the channel, right? So Alice can prepare a bipartite state. Call this A, call this R. Send A to the channel input, right? And then out comes B. That returns to Alice. And then she can perform a joint measurement, right? So just like the trace distance is the related to the minimal guessing probability, the same is true here. You know, there's a way to express the optimal guessing probability to guess correctly in terms of the diamond distance. Okay, and so this has been studied a fair amount. It's an important concept both for quantum information and quantum computation. In quantum computation, you're trying to realize quantum gates, quantum logic gates. So in that scenario, N would be like an ideal unitary that you're trying to realize, like C naught, Hadamard, T gate. Those are the gates that are universal for quantum computing. And then there's a noisy version of it. This is a worst case error metric. You know, it says, it talks about, it expresses the deviation between the channels over all possible inputs. And so diamond distance is used in the proof of fault-tolerant quantum computing threshold theorems. You know, so it's an important concept across the board in quantum information science. Okay, and then similar to diamond distance, you can define channel fidelity. So channel fidelity is just this. Remember, channel fidelity is a similarity measure. Trace distance is a distinguishability measure. So they're always the opposite of each other. And then that means the soup will turn to an imp. Okay. So fidelity of channels is defined like this. And the same argument applies to, you can conclude that the nth can be replaced with a minimum over pure states, such as the reference system is isomorphic to the channel input system. Both the diamond distance and the channel fidelity can be computed by semi-definite programs. Right? So I'm not going to go over that here, but it's done in the book, complete derivations. You're welcome to study it and ask questions in office hours. I'm feeling pressure in this course. We're in what, end of October? We have to get to like communication protocols. That was the whole goal. Right? I'm trying to pick up the pace. We're going to do entropies this week. And I think we're just going to dive right into communication. All right. Any questions about this stuff? This is a very brief overview of these concepts. All right. We're going to move on to quantum entropies. A long time ago, we talked about Shannon's entropy of a probability distribution. The story that I told in that original lecture was that actually von Neumann defined entropy first, right? And he defined quantum entropy, which generalizes Shannon entropy. And that's the reason why Shannon called that function that he thought he invented entropy. Okay, so it's called von Neumann entropy. Or simply quantum entropy. And it's defined like this. Usually we use system labels, right? Because for a single density operator, if you want its entropy, maybe it's not necessary to put the system labels, but it's very helpful later on. So we'll use this notation. This is actually a mathematically good notation because entropy is a function of the density operator. Right? What function is that? Negative trace rho log rho. In this class, we use log base 2 because we want to measure entropy in qubits. Okay? We're going to be thinking about like data compression, qubits per copy of the source. That's the kind of units of data compression. Channel coding is number of qubits you could send per channel. So we're always measuring in qubits. Yeah.
Like the physical difference or like practical difference between different log bases. Like how does that come out? Like we use log bases.
Yeah, so like I would say that if you're doing physics and not information theory, though one could argue that those are actually the same. But at the end of in this class, we're using log base 2 because everything's in terms of bits. Like if we plug in the maximum mixed state, we'll get log D, right? And so if we have a dimension 2 system, it'll be one entropy of 1 qubit. Right? And so that's the only thing. It's just like we want to say bits here. It's where in standard physics you just use natural log because you're taking derivatives a lot, and it's very convenient not to carry around extra factors. It's the natural law. So for some of the proofs that we'll do, we will just convert to natural log because I don't want to write like natural log of 2 everywhere. Right? So, but whenever we study communication protocols, it'll be log-based stuff. Good. Another notation that we use a lot is this. And one could debate the merits of this notation, but it's standard. It's inspired by Shannon's notation. Remember, Shannon's notation for entropy of a random variable x was this. And the whole thing about entropy is that it's a function exclusively of the probability distribution not the underlying values. And so that's why that notation could be a little disturbing. But at least in the quantum case, we put the subscript to like remind you of which density operator, for which density operator we're computing the entropy. The system label is helpful when we go to multi-partite density operators and we're taking, there are certain information quantities we'll study in a minute that are linear combinations of entropies of the marginals. And then there it's helpful to have the system label. Okay, so you can do a calculation using the tools that you've learned so far. And you'll realize, well, if rho has a spectral decomposition like this, then the entropy is exclusively a function of the eigenvalues. And it's actually equal to the Shannon entropy of the eigenvalues. Okay. So yeah, that follows from a quick calculation. It also tells us that the entropy is invariant under isometry. Right? If we do an isometric rotation of the state, that doesn't change the eigenvalues. So the entropy doesn't change. So that's very nice. We take the convention that 0 log 0 equals 0. Why do we do that? Well, from a continuity argument, we take the limit of x going to x log x, or x is going to 0, that's 0. Simply because x goes faster to 0 than log blows down, I guess, to negative infinity. Okay. Entropy is a measure of disorder. It has a fundamental operational interpretation in quantum information theory is the limit of quantum data compression. There's a generalization of Shannon's theorem. It was done by Schumacher in 1995. That's actually not done in the book. It's not done in the book with Sumit. It's done in my first book. I'm debating whether I'll go over it. It is an important theorem, so I feel like we should go over that. Okay. So what the theorem says is that, given many n quantum systems, they're in the state rho tensor n. That's like a quantum data source, just like we had an information source for Shannon's theorem. For such a source, there's a question of the number of qubits, the rate at which you need qubits to represent the state faithfully. And what the theorem states is that the limit of data compression is the quantum entropy. So number of qubits you need per copy of the source to transmit it over perfect qubit channels and reconstruct it with error tending to 0 as n gets large. That's the von Neumann entropy. So the theorem says that there exists a scheme to achieve that rate. And if you try to compress at a rate lower than that amount, then you can't do it. The error necessarily blows up to 1. Okay. So that's its interpretation in a few words. There's another interpretation of it in entanglement theory. So this I'll also talk about in words. It is something that's done in my first book. We didn't do it in this second book. But there's a question of, suppose you have a pure state and many copies. There's a question of, by using a set of operations called local operations in classical communication, So what are local operations in classical communication? I don't think we've talked about that in the class so far. Maybe in the context of teleportation. So LSCC is like a set of operations where they go back and forth. Alice does a measurement, sends classical data to Bob. Bob then does a measurement condition on that. They go back and forth. And then there are these like local quantum registers they can hold on to. So this can go on and on. There's some finite, arbitrarily large number of rounds. And at the final it's called this A hat and B hat. So they're trying to convert this state to maximal entanglement. Okay. Maybe this is a weakly entangled source, but it's a pure state. They're trying to convert it to a maximum entangled state. The rate at which they can convert n copies of this to maximal entanglement, the optimal rate is also the entropy of the reduced state. Okay? So that's why it's called entropy of entanglement. So that's the other fundamental meaning of entropy in quantum information theory. There are others that people have explored in the context of resource theories and more related to thermodynamics, where entropy was originally invented and used. Okay, but those are the two. Just right now, entropy is the quantum data conversion limit. And this optimal rate that we're talking about is called distillable entanglement. Or pure state. Okay. Why would you be interested in distilling maximal entanglement? Well, we saw at least, well, we saw 3 examples. Right? Teleportation, you need maximal entanglement. Same for superdense coding. Then we talked about the CHSH game. So in that game, you need maximal entanglement as well. And then CHSH game has applications in quantum key distribution. So that's why you'd be interested in those things. Okay. So let's leave that at that for now. I want to talk about other entropies that are derived from the basic one. There's conditional entropy. You write it like this. So it's of a bipartite state. Right? What you do is you take the joint entropy and you subtract the marginal entropy. Right? So that's where this notation with system labels comes in handy. So this conditional entropy is somehow an abbreviation for this one. We put the bar, right? We put the vertical bar. That's analogous to what we do with probability theory, right? For conditional probability, we put a bar. What does it mean? The probability of this given that. Right? The probability that it's sunny given the weather prediction. Right? So there's a similar interpretation going on with conditional entropy. You can think of this as the uncertainty. So suppose that there's this bipartite situation. Alice and Bob And Bob possesses the B system. And so you can think of this conditional entropy as the uncertainty that Bob has about A, given that he possesses his B system. Okay. Entropy itself, you could think of like this scenario. There's row A, and then there's Bob over here. But in this situation, Bob has nothing, right? So the usual entropy is just about the uncertainty that someone has about a system if they don't have access to anything. Okay? But conditional entropy, it's really like uncertainty about Alice's system from the perspective of Bob. Okay? And this also has an operational meaning. Okay? That's a very beautiful one. But it essentially has this meaning, like in a variation of quantum data compression. Okay, so supposing you allow classical communication for free, it's the rate at which Alice would need to send qubits to Bob, such that he can reconstruct the joint states using his system B as quantum side information. Okay, that's a task called state merging. And the interesting thing about conditional entropy is, in the quantum case, is that it can go negative. Okay, so this is a huge difference between classical and quantum. It's worth pausing and discussing this. Conditional entropy in quantum information theory can go negative. And if that happens, it's a signature of entanglement. Okay. So let's look at an example. Consider the maximum entangled state. What is its conditional entropy? So we have to compute the entropy of phi itself. Okay? Phi is a pure state. Okay? What is the entropy of a pure state? I know you know it. All right, so it's zero. Okay, why is that? Well, there's only, for a pure state, there's only one eigenvalue equal to 1. Right? 1 log 1 is 0. And then all the other eigenvalues are 0. And then we take this convention 0. Okay? So the entropy of a pure state is equal to 0. You get just by plugging in. So that means that the entropy of phi is equal to 0. Right? Now, what is the entropy of B? Well, what is the reduced state of the maximum entangled state? Maximum mixed. Good. So if we take trace over A, phi, some of you had this kind of thing as a homework exercise. We use this notation pi. That's just identity over the dimension of B. So for the maximum mixed state, all the eigenvalues are the same and equal to 1 over D. You plug in the formula and you get log of D, logarithm of the number of degrees of freedom. So that's like number of qubits in the B system. So what does that mean? The conditional entropy goes negative. Negative log of D. All right. Let's pause a bit and remember why the conditional entropy in classical information theory is positive or not negative. So the conditional entropy in classical information theory was defined like this. It's an average of the individual entropies using the conditional distribution. Okay. And I believe we talked about it. You know, the formula for entropy in classical information is the same. At least this formulation is the same. And this is the formulation we use to get this definition. Okay? But in the classical case, it can be understood as a convex combination of entropies of conditional random variables for a fixed realization of the random variable big Y. Okay, so each of these are non-negative, and then we have a convex combination non-negative, so the whole thing's non-negative. All right. So that's why classical conditional entropy is always non-negative. All right.
You can see that also from the first inequality, right? Because log 2 of the conditional probability distribution should be, I mean, the conditional probability distribution is lower than 1, right? As a probability.
Yeah. Yeah, I mean, that's the reason that entropy itself is non-negative. Okay, so what does this tell you? It tells you in the quantum case, the conditional entropy, you cannot always write it as a convex combination of entropies. Otherwise, it'd be non-negative. We just showed it's negative for some states. Okay. So that's a key difference. All right. And then I don't know if we'll get to it, but you know, if a state, what you can show is that if rho AB is a separable state, then the conditional entropy is non-negative. Okay, so that's a basic fact. And remember, separable means unentangled. So if you take the contrapositive of this, what is the contrapositive? If the conditional entropy is negative, then the state's entangled. So that's the sense in which this is a signature of entanglement. Okay. Because the conditional entropy can go negative, it actually makes sense to think of its negative as its own quantity, right? So that might seem weird, but it's conceptually useful to do so. Okay? So there's a quantity that was defined by Nielsen and Schumacher. And you use this quantum notation and put in the wrangle, the angle bracket. Okay? So this is defined to be the negative of the conditional entropy. So H of B, and it's H of AB. And this is called coherent information. This quantity is fundamentally connected to the quantum capacity of the quantum channel. So the quantum capacity is the rate at which you can send qubits over a noisy channel, faithfully in the limit of many channel uses. So it really, you know, it has been an important quantity in quantum information theory, and because of that, even though it's the negative of that, it makes sense to just think of it as its own thing. All right. So if you evaluate coherent information, of the maximum entangled state, you get 5 log D. And then it's like, well, that state has log D events of entanglement. Right? So coming back to the operational interpretation of conditional entropy, here I'm just speaking in words. I don't know if we're going to get to the proof of this. If the conditional entropy is positive, remember we said we allow classical communication for free. Right? If the conditional entropy is positive, then you need to consume qubits at this rate to transfer the A system to the B system. Okay? To Bob. If the conditional entropy is negative, then you actually don't need to send any qubits at all. And the conditional entropy, the negative of it, becomes the rate at which you gain entanglement. You can extract maximally entangled states from the state at the rate equal to the conditional entropy while transferring the system. Okay, so that was a very beautiful result. Actually, one of the few theoretical results in quantum information published in Nature, Nature Journal, Nature Magazine, whatever you want to call it. But it was a very important insight. Okay, so that's conditional entropy, coherent information. There is a quantum generalization of mutual information, and there we use the same formula. The same formula as Shannon. So you take marginals and subtract the joint entropy, and that's mutual information. All right. This, I think to interpret this, it's most helpful to rewrite it in terms of relative entropy. Right? We talked about quantum relative entropy previously. So you can do a calculation to check this. And remember that relative entropy is a distinguishability measure. We're going to be talking about it in more detail today. Probably also. So relative entropy is like a pseudo distance. It's not a true distance because it's not symmetric. It also doesn't obey the triangle inequality. But for all states, it's non-negative, and it's equal to 0 if and only if the states are the same. Okay? So you can intuitively think of mutual information as a correlation measure. How far it puts this rho AB from a product state. That's what it measures. Right? That you see with the relative entropy, if you think of it as like pseudo distance. So if the state is indeed a product state, it will be equal to 0. But if there's any correlation whatsoever, it'll be strictly non-zero. Okay. And you can also place upper bounds on it in terms of the log of the local dimensions. Right? That we won't get to today.
Is it from all product scale or this particular one? Like we write it as a.
So that's a good question. You can also prove this. This is not true of general measures, but it's true for relative entropy. You can prove this. So this answers your question. Right? From an arbitrary constant. That's an equality that holds. It's a special property of quantum relative entropy. If you substitute in trace distance, that does not necessarily hold. All right. And it just has to do with the way that logarithms of product states combine, and like the algebra you can do with logarithm. Okay. We'll soon be recalling, why don't we just recall relative entropy? Just a reminder of this formula we studied before in the context of the quantum Stein type. Okay. The final one I want to define is conditional mutual information. This is for a tripartite state. So what do? The way to remember, question, yeah. Good question. Relative entropy has a specific formula. Okay? Generalized divergence is just a general concept. And yeah, I made the notation similar. It's inspired from relative entropy. The only thing required for generalized divergence, I'll put like this underscore for generalized divergence in the book, we make it bold. Quantity, we call it generalized divergence if it obeys the data processing inequality. That's the only requirement that we make. All right. And so, trace distance is a special case. Relative entropy is a special case. If you take the negative of fidelity, that's a special case. We talked about Renyi relative entropies. That's a special case. It's just a concept that we use throughout the book to emphasize that many things can be proved from data processing. Okay? So my plan is to give you all a common homework 5. Basically, I'm going to choose some exercises from my previous book about entropies to get to play around with them. And the thing to remember, the way to think about these problems is, can I solve them using data processing? Can I reduce it to data processing? That is so powerful that many things can be proven from that alone. And so the reason we use this in the book is to emphasize that very point, that much of these things can be thought of simply in terms of data processing. And you might have to do some tricky rewriting, but ultimately you can rewrite in terms of data processing. Many a paper has been published in quantum information just based on data processing. So, yeah, I don't think that moment is gone. I think there's still many things to be done. Okay, conditional mutual information. What you do is you take these formulas and you just condition on the C system. Right? So it's literally this, and it's for a tripartite state. This is also a very interesting quantity and quantum information theory. I think all the quantities are interesting, but things become perhaps especially interesting when you're conditioning on a quantum system. Okay? Here we saw in the classical case, if you're conditioning on a classical system, then you can rewrite as a convex combination of entropies. Okay? Why don't we return to this point? So suppose that really the V system is classical. Remember we talked about classical quantum states. So suppose that we can write the state like this. Tensor that's the flip of what we usually put the classical first and then the quantum on the right, but you know, same thing. So if the bipartite state has this form, then what you can prove is that the quantum conditional entropy indeed reduces to a convex combination of entropies of these states. Okay, just like the classical case. And a classical quantum state is a special case of a separable state. So this, everything's consistent. Okay. For conditional mutual information, it's a similar story. For the fully classical case, conditional mutual information is somehow a little more trivial. It is a convex combination of mutual information. Okay? The condition on a classical system. Like we could have, you know, random variable with distribution, joint distribution x, y, z, and then we could replace ABC with x, y, z, and we could write this as pxy given z and pz. Right? We could factor it into a conditional distribution on a marginal. And then the conditional mutual information would just be a convex combination of mutual informations of these. Right? Similar to what was happening here. Right? Except now it would be conditioned on z. And so that's how things are for the classical case. For the quantum case in general, you can't do it. Okay? Similar to how in general, for quantum conditional entropy, you can't do it either. One of the most important inequalities in quantum information is data processing for relative entropy. I mean, and that's why it's a generalized divergence. Eventually, we'll get to the proof of that. That can be used to show that conditional mutual information is non-negative for all tripartite states. That's a very important inequality, and it goes by the name strong subadditivity of entropy. Okay? And then that implies that mutual information is non-negative also. You can recover mutual information from conditional mutual information by taking C to be a trivial system. Or if C is in tensor product with the state on A and B, then conditional mutual information collapses to mutual information. All right. Any questions? Yeah.
Is the conditional mutual information related to like in the system kind of thing?
Yeah.
Measure how much they have trying to reach on to make.
Yeah. So that is precisely the right idea. You can construct an entanglement measure based on conditional mutual information. You can think of C as an eavesdropper. And this is, we forgot to mention the interpretation of conditional mutual information. You can think of it as a measure of correlation between Alice and Bob from the perspective of C. And so if C becomes an eavesdropper, then it's directly related to secret key. And it also ends up being related to entanglement between A and B. Okay. Yeah, but it's, I think you said something like uncertainty measure. It's more like correlation measure. But you can also think of it as like reduction in uncertainty. Yeah. And that might have been what you were thinking of.
Yeah, because the nature of correlation, not like an actual uncertainty. I was thinking in terms of it.
Yeah. Yes. You can also rewrite mutual information like this. Just use definitions, right? But then this leads to an interpretation. It's like the reduction and the uncertainty about A from the perspective of all. Some people like to draw Venn diagrams to illustrate entropies, but I will say on the record that I hate that. Strong word, apparently not. I will say it. Especially if you're trying to like prove things. Okay, so let's move on to discuss relative entropy in more detail. Okay, so the formal definition of relative entropy, I believe we wrote it before. So it's the formula we just wrote in a certain case, in the case of interest. If the support of rho is contained in the support of sigma. Okay, and that's plus infinity otherwise. Okay, and we allow, all throughout the book, we allow rho to be a density operator. And sigma, we allow more generally to be a positive semi-definite operator. That's very useful because we'll be able to recover, we defined all kinds of entropies. We defined entropy, conditional entropy, coherent information, mutual information, conditional mutual information. All of those can be recovered from quantum relative entropy if you allow sigma to be more generally positive semi-definite. Okay, so I want to give you a sense of why this formula is the way it is from a kind of physical argument. So the argument is this. If you take the limit as epsilon goes to 0, of this, then the formulas are consistent. Okay. So remember, sigma plus epsilon I is positive definite. For all epsilon strictly greater than 0. Right? That is a wonderful trick to make any operator invertible or positive definite. Just add a little bit of the identity. We use that all the time, right? For all kinds of things. So, you know, what does this mean? Well, if you're always plugging in a positive definite operator, then you're using this formula. All right. So, what this equality is stating is that if support of rho is contained in support of sigma, then in the limit, you know, this quantity will converge to this formula. Whereas if this support condition does not hold, then the quantity actually converges to plus infinity. That's what it says. Okay. Why is this relevant from like a physical perspective? Well, think of sigma as a state, right? And then if you're adding identity, it's like you're adding a little bit of the maximum mixed state. And so you would expect, like from I don't know, basic things that we observe about the universe that are like, you know, formulas that should be nice. That this is asserting that, you know, in the limit as the noise goes to 0, as the noise that we're adding into the state goes to zero, then we want to know what will happen, because that's like the quantity evaluated for the true states. And then you can actually get into philosophical arguments like, well, does any state, do pure states actually exist? Right? Would you ever observe a pure state, a true pure state experiment? There's always like a little bit of noise, and then you can't control it. Anyway, so that's the point of this. And then I think this helps to clarify this kind of complicated, what might seem like a complicated mess in the definition of the formula. Okay. So I'd like us to prove this, and I don't know how long it'll take, but it's not so bad. So we'll prove this. The basic idea is to decompose the Hilbert space. There's an underlying Hilbert space on which rho and sigma act, right? And if it's not defined, then you can define it just to be the unit of the support of the operators. Okay. So you decompose the Hilbert space as a direct sum of the support of sigma and its kernel. Right? These are two orthogonal subspaces. And so you can decompose in this way. So let's let pi sigma be the projection onto the support of sigma, and pi sigma complement will be the projection onto the kernel. Okay? Yeah. Okay. So what does this mean? We could take rho and we can write it as a 2x2 block matrix, right? So, and there are four like submatrices to consider. So you can sandwich rho by pi sigma twice, call that rho 0, 0. You can sandwich it by pi sigma per, call that rho 0, 1. The other way, rho 1, 0. So that's actually rho 0, 1 dagger. And then pi sigma per rho, pi sigma per. All these are perps. Rho 1, 1. So that means that rho, we can write it as a 2x2 block matrix. Okay, we can do a similar thing for sigma, but the situation for sigma is that its block decomposition will actually look like this. The zeros elsewhere, right? Because pi sigma is the projection onto the support of sigma, right? And so this might seem funny what we're doing here, but this is how we write it with respect to this decomposition, right? So if we go through the same exercise for sigma, pi sigma sandwiched by pi sigma is simply sigma. And then sigma, if you right or left multiply it by pi sigma per, that's the kernel. And so it's 0. So that's why we get this. All right. So now, to think about this limit, it suffices to think about this limit. Right, because plus epsilon identity. Because the epsilon identity only appears in the second argument. So the question will be all about like what is the convergence of this quantity? The proof boils down to that. So let's just think about the different cases. Why do we make a little space? Okay, so we want to think about, let's first suppose we're going to put a star for the support condition. Suppose that the support condition holds. Well, what does that mean? If the support condition holds, supportive rho is contained in supportive sigma. So if you sandwich rho, if you right multiply by the projection onto the kernel of sigma, then you'll get 0, right? So this means that rho 0, 1 is 0, rho 1, 0 is 0, and rho 1, 1 is 0. Those are all zeros, all right? So the whole situation kind of simplifies. And let's just do this calculation. Trace rho log sigma plus epsilon identity. Now let's use the block matrices. In this special case, I'll just write everything because we're going to repeat the argument for the case where there's the support condition does not hold. Okay, now we have to add an epsilon identity. The identity decomposes as the projection onto the support plus the projection onto the kernel. Right? That's the full space. We add those together. You get identity. So then what does that mean? Sigma plus epsilon identity. Okay, and then in the block form, that means that identity can be written as pi sigma prime. That helps you to visualize it better as a matrix. Right? Okay. Then, if you multiply by epsilon and add to sigma, you get this. Sigma plus epsilon pi sigma, epsilon pi sigma per. Okay. Then logarithm of a block matrix is the block matrix consistent of the logarithm of those matrices. We have this. Okay. Now in the special case that we're considering, where all these matrices are 0, actually, why don't we just do the next calculation? Trace will be the sum of the traces of these. This times this and this times this. Right? That's what happens when we do the calculation. Okay. So now, if this condition applies, okay. And then if you take the limit, point is that it's but this is now like safely contained in the support, and so when you take the limit as epsilon goes to 0, there's something there, right? The sigma is still there, and so it reduces to a finite quantity. Reduces to a finite quantity. Okay. And in the special case, when the support condition holds, it means that rho 0, 0 is equal to rho. You have a similar situation that we drew for sigma, because sigma is contained within its own support. Okay, so then you'll just get trace of rho log sigma. And then it's precisely the right thing, consistent with this formula for that second center. Okay? So that's kind of like the simple case. Now, the star does not hold. Then rho 1, 1 is non-zero. That's the basic thing you can conclude. There's something there. And the problem then becomes this second term. That's where you get the blow. So, yeah, log of epsilon times a projector, that's just like log of epsilon scalar can factor out, because this has eigenvalues 1. Right? The eigenvalues of the projector are 1. So this expression, let's just write it, rho 1, 1. This becomes equal to log base 2 epsilon, and then trace rho 1, 1. Log, log small. I sigma per. Okay. And the point is that this number right here is strictly greater than 0. Okay. So then when you take the limit of this expression, as epsilon goes to 0, you'll get minus infinity, right? Limit of log epsilon as epsilon goes to 0 is minus infinity. Okay? So that's the basic idea. And we could have done things where we said, this is the definition of relative entropy. And then, oh, it reduces to this. But I don't know, just depends on your perspective, but which one is more complicated. So yeah, the basic thing with relative entropy is just to remember that it can be infinity sometimes. You need to check with that. Very recently with a student working a paper, and we forgot that. We rewrite a lot of the paper. So don't forget. Okay. About 8 minutes. Any questions about this? All right. I think there might be other ways to prove this, but I mean, this is the basic idea. So there's other things I want to show you about relative entropy. So if we have spectral decompositions of rho and sigma, you can show that the formula for relative entropy collapses to this, where it actually starts looking a bit like the formula for classical relative entropy. Just as a reminder, suppose you have distributions lambda I and mu I. The classical relative entropy is this. There's a single index. So this one, they look like each other. Actually, you can define some distributions to make this more precise. Okay, so let's define distributions. We call them RJK and SJK. RJK will be this. Okay. This will be a joint probability distribution. SJK will be QK. Right? So the interpretation here is PJ is RJ, like a marginal, and this quantity becomes like a conditional, K given J. All right? So you can prove that it's a conditional distribution. Each of these terms is non-negative. If you sum over K, you can use the fact that the phi K's are an orthonormal basis to get that they sum to 1. Right? This one you think of as in the conditional probability in the opposite way, SK and SJ given K. Right? So this here becomes the marginal, and this SJ given K is the conditional. And for a similar reason, this is conditional distribution. If you're non-negative, if you sum over J, you'll also get 1. Okay? So this here is a matrix, and it's called doubly stochastic, because it's a stochastic matrix if you sum over the rows or if you sum over the columns. Okay, so now you can see in this formula, we can, in the log part, divide and multiply and divide by this quantity. And then we can assert that, well, this is equal to the relative entropy, the classical relative entropy of R and S. So that's very interesting, and it gives a link between classical and quantum relative entropies. And this fact has been used in some highly non-trivial proofs of properties of relative entropy, of quantum relative entropy. All right, we're about 3 minutes out. I think we should, the natural stopping point. I was about to get into properties of relative entropy. So if there are any questions about any of this, we can talk about it. All right. I'll see you Wednesday. I think our homework's due on Wednesday, right? If there are questions, come to the office hours today. All right.